So now I'd like to turn to the first session of our symposium. So it is my great pleasure to introduce our first invited speaker of the symposium, Jeannette Wing. Jeannette is the Avanessians Director of the Data Science Institute and a Professor of Computer Science at Columbia University. Before joining Columbia in 2017, she served as the Corporate Vice President of Microsoft Research, overseeing a global network of research labs. She's widely recognized for her intellectual leadership in computer science, particularly in trustworthy computing. Jeannette's seminal essay titled Computational Thinking was published more than a decade ago and is credited with helping establish the centrality of computer science to problem solving in fields where previously had not been embraced. Before joining Microsoft, Jeannette was a faculty member at Carnegie Mellon Computer Science Department, where she served as the head of the department and as Associate Dean for Academic Affairs in the School of Computer Science. She also spent time with the National Science Foundation, where she was the Assistant Director of the Computer and Information Science and Engineering Directorate. And prior to joining Carnegie Mellon, Jeannette was a faculty member here at USC in the Computer Science Department. Jeannette is a fellow of the American Academy of Arts and Sciences, American Association for the Advancement of Science, the Association for Computing Machinery, and the Institute of Electrical and Electronic Engineers. She holds bachelor's, master's, and doctoral degrees from MIT. The title of her talk today is Data for Good, Ensuring the Responsible Use of Data to Benefit Society. So a big welcome to Professor Jeannette Wing. Welcome, Jeannette.
Thank you, Craig. Thank you, Yolanda. I first of all want to wish ISI happy birthday. 50 years is quite an impressive feat, and I want to share with the audience that as a graduate student, I spent a summer at ISI. I don't know if you knew that, Craig.
No, I didn't know.
But I actually had the luxury of sitting in Ralph London's office with a view that was similar to what I think is behind you. It was gorgeous. And of course, I do remember my years at USC, and it's wonderful to be talking to the USC audience again. So fond memories all around. Okay, so I will start my talk. As Craig said, I'm going to talk about data for good, ensuring the responsible use of data to benefit society, which is part of the mission statement of the Data Science Institute here at Columbia University. I want to start by putting into context what I think data science spans, and that, of course, starts with the data life cycle. We generate lots and lots of data, and data science in some sense is not new in that for many decades, the sciences have been generating lots of data through large scientific instruments like telescopes in the sky and Large Hadron Colliders and neutrino detectors in the South Pole and so on. What is new, of course, is that a lot of the data that we are generating today is generated by us. So data generated by people is causing a revolution in data science. We collect the data, and we don't always collect all the data we generate. We process the data. By processing here, I mean everything from encryption to compression, but also the more mundane tasks, but important tasks of data wrangling and data cleaning. We need to store the data in some medium, and we store the data in such a way so that we can retrieve the data efficiently later, and that's where database management and data management techniques come to play. Of course, what is so exciting, or what is making data science so exciting today, is all the analysis that we're able to do with the volumes and types of data we have. So under data analysis, I put in AI, machine learning, all the statistical and computational techniques that people are studying in all the wonderful programs that you mentioned. It's not enough to analyze the data, of course. We have to visualize the results. After all, spitting out probabilities is not very informative. But it was not until I joined Columbia University and talked to my colleagues at the journalism school where I came to appreciate what I call data interpretation. In other words, yes, we absolutely have to visualize the data, but even showing a pie chart or a bar graph is not enough. One has to tell a story about what is it that I'm supposed to be getting out of this visualization, and in the end, what is it that I'm supposed to be getting out of the analysis. And throughout this data life cycle, I want to emphasize the importance of privacy and ethical concerns in collecting the data, analyzing the data, and of course, telling stories about the data, especially when the data is about people. So what is data science? I would like to share with you a succinct definition of data science. Data science is the study of extracting value from data. And the most important word in this definition is value. Value is subject to the interpretation of the end user. So to a scientist, value is discovering new knowledge, finding another exoplanet. To a business, value is calculable. It's bottom line. It's an asset. Data is an asset that you can assign a particular dollar amount to. Or every time some user clicks on a link, someone is making money from that. There is value to that data being collected. Or value to a policymaker is really a value in terms of helping the policymaker decide whether to, say, change the city zoning so that new houses aren't built on the coast. So value is subject to the interpretation of the end user. Extracting is also an important word in this definition. All the phases of the life cycle I showed in the previous slide go to extracting the value from the data. And as you know, it takes a lot of work to extract that value. So I want to share with you the three-part mission statement that I have for the Data Science Institute at Columbia. The first is to advance the state of the art in data science. This is about pushing the frontiers of basic research. And of course, data science is, in some sense, a new emerging field in that it's the convergence of computer science, statistics, mathematics, operations research, etc. So even this part of the mission statement speaks to defining what data science will evolve to be. The second part of my mission statement speaks to the breadth of Columbia University, and that is to transform all fields, professions, and sectors through the application of data science. Since all fields, professions, and sectors have data, and data now is in digital form, the applicability of data science holds for everyone. And finally, the third part of my mission statement is, in fact, the title of my talk, and that is to ensure the responsible use of data to benefit society. And by this, I mean two things. First, to benefit society means addressing societal grand challenges like climate and health and energy and social justice. And responsible use of data brings in the importance of privacy and ethical concerns. And so I summarized this three-part mission statement into three words: data for good, data to do good for society and humanity, and using data in a good manner, responsibly, ethically, and so on. At Columbia University, the Data Science Institute collaborates with all 18 schools, colleges, and institutes throughout the entire university. So every single school is represented here, and we even collaborate with Barnard College and Teachers College. And so many of the engineering departments, arts and science departments are collaborators, but so are many of all the schools on the medical campus, and then other schools like law and business, social work, journalism, and so on. DSI has 5 focus areas: foundations of data science, health, social justice, business and finance, and climate. And from a grassroots perspective, we have 11 centers and working groups that focus on themes that are of interest to the faculty. So we have a theme on smart cities, one on health analytics, and so on. One program that the DSI runs in collaboration with Columbia Entrepreneurship is called the Collaboratory. And this is where we encourage faculty from different disciplines to come together and co-design and co-teach a course where data science is one key component of the course. And I just want to highlight two examples. One is an undergraduate course, which is called Data Past, Present, and Future. And this is co-taught by a professor in applied math and a professor in history. And it's a gentle introduction to data science, but it's not a rinky-dink course in that on the first day, the students are opening up a Jupyter notebook. The other success story in this program is in the business school, where a sequence of 10 courses was designed for business school students, so that now over 50% of all MBAs coming out of Columbia Business School have some data science knowledge. I wanted to also say that the Data Science Institute has a robust industry affiliates program. At any point in time, we have about 25 companies who are members. And we have a very special relationship with IBM. Columbia and IBM have a long-standing relationship. And we have a center on blockchain and data transparency. So what I want to do in the remaining time is to actually tell you some stories about the research going on in the Data Science Institute at Columbia as a way to convey some of the depth of the research we do, pushing the frontiers of methods in data science, showing the applicability of data science in all fields, and talking a bit about the issues of responsible data science and societal grand challenges. So let me start with one story on advancing the state of the art in data science. And it has to do with causal reasoning. As many people in the audience know, data science that borrows from machine learning and other AI techniques, especially in machine learning, it's very good for showing correlation, but not causality. And I think the next big thing, or the next frontier for data science methods, is to look at how machine learning and causal inference and big data can all come together. Because if you think about some of the disciplines like medicine, economics, political science, sociology, they don't want just correlation, they want causality. So in this particular work, I want to talk about the problem of, the problem of multiple causal inference. Now, in classical causal inference, one considers univariate causes, whether a subject receives a drug or control. The problem that Jeannette Wing and David Bly address in this particular work is a situation where there are multiple causes for an effect. And it turns out that this is not only a common scenario, but it's an easier problem to solve with weaker assumptions than for classical causal inference. So let me just give you an example. Suppose I am a movie director and I'm trying to decide which actors to cast in my movie. I want to predict how much money will my movie make dependent on this cast of characters, a cast of actors. The actors are the multiple causes, the revenue is the effect. And one could express this goal in terms of the potential outcomes formulation from statistics. Or if you're more of a computer scientist, you might express it in the do calculus of Pearl. The fundamental problem in causal inference is due to unobserved confounders. These are variables that affect both the causes and the effect. For example, the genre of a movie could be a confounder, as action movies make more money than artsy movies. Whether a movie is a sequel or not is a confounder. The fact that some actors, when appearing together, might generate more revenue than if only one were cast alone is a confounder. So a naive approach to solving this problem, or calculating the potential outcome, the revenue here, is to fit a regression from actors to revenue. This estimates how much revenue changes when an actor is included. The problem is, of course, because of unfounded confounders, confounders bias the regression coefficients. So some actors will be overestimated and some actors will be underestimated. Now, I want to just mention that there are many applications to multiple causal inference. For instance, asking the question, how do genes affect a trait? Or how do sports players affect how well a team is doing? Or how do the prices in a supermarket affect how much money a customer will spend? So in classical causal inference, the procedure usually goes like this. You think about all the confounders, and this is the manual human ingenuity step. And once you believe you've thought of all the confounders, then you can measure the confounders and estimate the causal effect in the expression on the upper right here. But there's a huge assumption for this technique to actually be sensible. And that is what's called the strong ignorability assumption, which is that there are no unobserved confounders. And so the assumption rests on step one, where we rely on the human to have thought of all the confounders. And if the human has missed something, then all of the subsequent calculation is on shaky territory. Well, the new idea is to this notion of a deconfounder. And the procedure goes slightly differently. First, you fit a local latent variable model of the assigned causes. So you build a factor model, and you can actually test whether this model is good or not, given some objective function. And then from the model, you can infer the latent variable for each data point. This is the substitute confounder. And then we correct for the substitute confounder as in the previous case, estimating the causal effects, again, as in the upper right-hand equation. Now, this doesn't come for free, but there is still an assumption, but it's a weaker assumption. And the weaker assumption is that there's no unobserved single cause confounder. And the other good thing about this procedure is that after we build a factor model, let's say, we can actually check to see whether it's good or not. So unlike the untestable assumption that we had in single causal inference, we have something we can actually check. And then we can prove that the deconfounder actually gives an unbiased causal inference. So back to the movies, with this procedure of creating this deconfounder, we can show that with the deconfounder in this James Bond movie, Sean Connery's value goes up, and the actors who play M and Q, their values go down. And this basically says that without the deconfounder, Sean Connery's value was underestimated, and the actors who played M and Q's values were overestimated, which makes sense because most people would go to see a James Bond movie to see Sean Connery. And then once you have this model, as for all causal inference, you can start asking and answering what-if questions. So the short summary is that this notion of a deconfounder corrects for unobserved confounders, like the genre, sequel, and so on of a movie. So let me go to a different way of approaching causal inference, and this comes from work that actually came from the economics community on synthetic control. And the idea here is the gold standard for inferring causality is through randomized controlled trials. This is, of course, what the medical community uses all the time when they're doing clinical trials. It's also what is behind A/B testing that the tech community uses. In synthetic control, it was the example I'm showing you here that came out of the original paper on this work, wanted to the original work wanted to show that Proposition 99 that was passed in California many years ago, that raised the cigarette tax on packets of cigarettes, actually helped reduce smoking in California. Now, there are many factors that could have helped reduce smoking in California, but the policymakers obviously want to say that there was a cause and effect. Passing Proposition 99 reduced smoking in California. So the idea behind synthetic control is you've got the real California, that's the actual California, but you construct a synthetic California out of basically weights of all other states. So for instance, you can imagine a synthetic California being built out of a little of New York, a little Massachusetts, and a little of Texas. So this idea of synthetic control was applied by my colleagues here at Columbia early last year, early during the COVID-19 pandemic last year, to determine what if the lockdown in New York State had been put in place earlier? Would we have saved lives? And they determined that, in fact, by creating a synthetic New York, they could show that there would have been lives saved had lockdown been put into place earlier than the governor had instituted it. And then later on, some epidemiologists in the School of Public Health, in fact, showed through their own analysis that lockdown delays cost at least 36,000 lives. My colleagues also wanted to do post-Memorial Day analysis, which is when there was a surge of cases, and they wanted to know what caused that. Was it because the temperatures, the weather was warmer and people went inside to escape the heat, or was it because of indoor dining and indoor bars? And in fact, it was because of indoor dining and indoor bars. So with this kind of synthetic control, one can do some causal inference. So that's all I wanted to say about some work in advancing the state of the art in data science. Perhaps the most important takeaway is that I do think that causal inference is the next big way for data science. Now, let me talk to you about some of the applications of data science. And let me start with probably the most obvious field that has been swimming in data for decades, since the Human Genome Project, if even before, and that is biology. In this work here, my colleagues were looking at the microbiome surrounding pancreatic cancer. And what they discovered was, through data analysis, was that the microbiome was counteracting the effect of the chemotherapy treatment that was meant to kill the tumor. So that's not good, because the microbiome was basically making the chemotherapy treatment ineffective. What they further discovered is that if you inject the tumor cells with an antibiotic, then that antibiotic would counteract the effect of the microbiome, therefore making the chemotherapy treatment effective. In a completely different application in astrophysics, some of my colleagues have been looking at predicting the cosmological parameters of the lambda cold dark matter model from weak gravitational lensing data. This is basically an interesting use of convolutional neural networks to see if the CNNs could better predict these parameters than off-the-shelf statistical techniques. And perhaps not surprisingly, although frustratingly, the CNNs did do better. Now, I say frustratingly because as with neural networks, we still don't know why they work so well, but in this particular case, they did. In a completely different area in economics, I wanted to talk about economics and machine learning a little bit, although I already mentioned it a bit. And part of my motivation is based on my time at Microsoft. When I was at Microsoft Research, I actually helped hire a bunch of economists. And when the economists collaborated with the AI and machine learning researchers, they realized that each could bring different techniques to each other. And what they found was the combination of the kind of causal inference that economists do via instrument variables and the big data that machine learning people like to analyze gave them a technique that, in fact, benefited Microsoft Business's bottom line. So I saw the value of economists coming together with computer scientists to do things that neither would normally have been able or even know to do alone. In this particular work, I wanted to share with you some a different work on bringing together economics and machine learning, and that is studying online markets and online work places, in particular Amazon Mechanical Turk. So these researchers actually, also including some people from Microsoft, looked at Amazon Mechanical Turkers in the US and India and analyzed all the data to determine what kind of model or what kind of marketplace did these online labor systems actually depict. And what they discovered is that these online labor markets behave more like monopsonies than, say, fair markets. And a monopsony, if you are not familiar with that term, is where you have one buyer and multiple sellers, the opposite of a monopoly, where you have one seller and multiple buyers. In a completely different area in finance, some of my colleagues in financial engineering have been looking at robo-advising. So if you happen to be very wealthy and you might have a personal financial advisor to help you determine how to invest your money. And as you know, individuals have different risk tolerances. So over time, your personal financial advisor will learn your investor preferences. Well, with robo-advising, it's very easy to use techniques like reinforcement learning to learn an investor's preferences. So what can basically be 8 or 9 iterations of an algorithm, which would take seconds to compute investor preferences, would normally take humans months or years to learn. In a completely different area in history, we have some very modern history professors at Columbia. These professors have been looking at analyzing large data sets of documents using topic modeling, sentiment analysis, and natural language processing more generally. In this particular example, the researchers amassed the largest set of declassified documents that the US government puts out every year. And they looked in particular at the cablegrams that were sent among the embassies in the 1970s to see if they could detect interesting events. So in other words, can we reverse engineer what historical events happen in a particular time period? And what they were able to do was show that they could easily distinguish between topics describing business as usual from those that deviate from such patterns. So every black dot here represents an interesting event, and you'll recognize some of them, like the evacuation of Saigon and the death of Mao Zedong. In work very recently by one of the DSI postdocs who's very interested in data and political science, he built an app for the last presidential election. Well, let's say that he built an app, and the last presidential election campaign for Biden actually adapted the app for their use. And this app is basically to help get out the vote. And so the insight is, if people were to text their friends, text to text through friends is more likely to nudge your friend to go and vote. And in fact, they were able to show in a causal manner that nudging friends was an effective way of getting more people to vote. In fact, as effective as the most manual and costly way that campaigns usually do it, which is door-to-door canvassing. Now let me turn to the last part of the mission statement, which is to talk about responsible use of data, and then later to benefit society. I have been advocating very recently a notion of trustworthy AI. And it really starts from trustworthy computing, which is an area of research that has been ongoing for at least 2 decades in industry, in academia, and funded by government. I know this because I helped fund it at the National Science Foundation. Trustworthy computing has come to mean a set of properties, including safety, security, privacy, reliability, availability, and usability. I argue that for AI systems, we have to add to this set of properties to argue trustworthiness, to argue their trustworthiness. So these properties are what machine learning experts would appeal to. For instance, accuracy. But they are beyond, getting an accurate classifier or accuracy in prediction. It's also about robustness, fairness, transparency, accountability, interpretability, explainability, and even ethics. And these issues are no longer just in the realm of, does this computer program do the right thing, which is really what trustworthy computing has all been about. But it's also about the consequences of a decision an AI system might make on people. And that's what complicates, if you will, the whole story of ensuring that AI systems are trustworthy. So in that vein, I wanted to talk about 2 examples on trustworthy AI. The first is some work that I have been doing most recently with some colleagues here on robustness and fairness. What we looked at is off-the-shelf FAIR classifiers, FAIR in terms of 2 notions of fairness, statistical parity, and equal odds. And what we found is that these FAIR classifiers are not very robust. It's very easy to very slightly change the distributions, the input distributions, and what is a FAIR classifier becomes an unfair classifier. So how can we tackle this situation? What we just did was we, in the spirit of what has been happening in the community more generally, adapted an online, a game theoretic algorithm, basically an online algorithm, so that we could build a class of robust FAIR classifiers. What's also novel about this work is that fairness is actually with respect to a class of input distributions, not just with respect to a single input distribution. And so this is just work showing that how easy it is for us to perturb the input distributions and just by reweighting them, and you'll see that there's almost no difference in terms of the weights, but the one goes from being a fair classifier to an unfair one. The second piece of work in terms of responsible AI and trustworthy AI is in terms of safety and security. And here is some work that was actually published in SOSP, a systems conference, that won the Best Paper Award. This is really to say that the systems community has really been embracing AI and machine learning and deep learning. In this particular work, again, in the spirit of perturbing inputs, they showed that it is very easy what they showed was they could build a system that could automatically generate changes to inputs that could make a system go from classifying something correctly to classifying something incorrectly. And they used two techniques from software engineering to do this work. One is, well, they were inspired by two techniques. In software engineering, there's a notion of code coverage. So they, in building Deep Explore, used the notion of neuron coverage to build this system. So the idea would be to make, in some sense, make sure you've covered all the paths in the neural network. The other technique they used that was inspired by software engineering is the notion of differential testing. And here the idea is if you have got two classifiers that are supposed to classify images for the same set of images, then you can compare how well the classifiers do against each other. So you look at how they are, where they're different. So with these two techniques that they were able to build the system that automatically generated changes to input images that were actually semantically meaningful for the task at hand, to show that many of the off-the-shelf, state-of-the-art DNNs for ImageNet and so on actually are easy to break. So now let me turn to data for good, tackling societal grand challenges. And the first example I wanted to explain to you is the work, again, done by a different DSI postdoc on data science and agriculture. In this particular work, he and his colleagues looked at 5 different crops planted in India. One should know that rice is probably the most planted and the most eaten grain in India. And what they showed that is, if by looking at the data and looking at how climate is going to change and affect the monsoon season, affect droughts, affect all sorts of ways in which are relevant for farming in India. If India's crop production continues to homogenize towards rice, then food supply in the country may actually be more vulnerable to increasingly frequent climate shocks. And so the idea would be to increase the share of production of other grains besides rice to dehomogenize the dependence on rice. And that can make India more resilient to these climate shocks. Now, the next step of this work is, of course, to take it to policy, to have government institute some kind of policy to help. And the last example I wanted to give is in healthcare. There's a huge effort going on worldwide called Odyssey. It involves 30 countries, 300 researchers, over 100 databases that have now collectively added up to 600 million unique patient records. So these are 600 million EHRs. And what's amazing about this work, especially for those of you who are computer scientists in the audience, all these records are in the same format. So once you have 600 million records in the same format available to you to analyze, you can ask all sorts of questions that you couldn't dream of asking before. And so based on this kind of work, they were able to, for instance, look at 3 diseases: diabetes, hypertension, and depression. And there were some interesting discoveries they made by just looking at the data. No clinical trials, just observational data. And first, let me tell you how to read this beautiful visualization. So you see these rings of rings. The way to read this is each ring of rings stands for a medical center. So the top middle ring here stands for Columbia University Medical Center, and if you were treated for hypertension, you're a radius in that ring of rings. The idea is then the inner ring represents the first drug that you were given as you were treated, say, for hypertension. If that doesn't work, then you're given a second drug, and that would be represented by the color in the second ring. If that doesn't work, you're given a third drug, and so on and so forth. And all these rings of rings actually stop after 4. Some of these radii go out for many, many lengths. So in any case, there are 2 interesting observations that I wanted to share with you that they discovered by just looking at the data. So one is with respect to hypertension. What they discovered is if you look at all the people in the study, and they studied at this point, they only had 250 million records. They looked at all the people treated for hypertension around the world. And what they discovered is that 1/4 of the people treated for hypertension were treated uniquely. In other words, which is, I think, a surprising percentage. In other words, if you are in that 1/4 and you've got hypertension, you're in that 1/4, and I'm your doctor, and you ask me, is there anyone else in the world being treated like me? The answer would be no. And that was pretty amazing to the researchers. Another interesting fact that came out of this work was looking at diabetes. For the most part, all the rings of rings looked like top 2 in this chart, with the drug metformin represented by the chartreuse ring being the first line of treatment, and for the most part successful. Except for the bottom ring of rings, you'll see that the colors look different. In fact, that JMDC represents a Japanese medical clinic. And what they observed is that, what they discovered was that the Japanese have a genetic disposition against metformin. So either the Japanese doctors knew not to give metformin as a first line of treatment, or they did, but they discovered it didn't work, and so subsequent drugs are needed to treat the diabetes. So I wanted to turn back to the opening story, which was on deconfounding and causal inference. With this incredible database of EHRs, you can do all sorts of things, including try to infer causality. And that's exactly what my colleagues did. The people who were looking at multiple causal inference connected with the Odyssey group, and they built a medical deconfounder, which is represented in the second expression on this chart. And just to cut to the chase, what they found was that they built 2 models based on patients who are being treated for diabetes. One was your typical model, and the other included the deconfounding term. And what they found is the deconfounder actually reduces both false positive and false negative rates. So for instance, acetaminophen, which is found in Tylenol, goes from causal to non-causal. And perhaps that makes intuitive sense because people are taking Tylenol or aspirin all the time. And, you know, why should that have the effect? And the other discovery was it goes the other way. So 2 particular drugs were found to actually go from non-causal to causal. Now, one challenge in this research is how do you validate these results? So what they were able to do was to look at all the PubMed literature and show that, in fact, the drugs identified to be causal through the medical deconfounder are more consistent with what the medical literature says. So that is the end of my talk. Just close by reminding you of my tagline, Data for Good. And I'm happy to take questions.
Okay, great. Thanks very much, Jeannette. It was a great talk, really interesting. So people, if they have questions, they can go ahead and post them in the Q&A, or the panelists can actually put them in the chat. But I'll start with a question first, which is, so you described some really interesting sort of techniques. I really like the stuff you talked about in terms of the causal reasoning, and then the visualization stuff is really interesting. You have all of these great tools available to you, and then you have all these interesting problems. How do you prioritize and decide what problems to actually work on?
So first of all, I don't do most of this work. All my colleagues do the work. I'm just reporting on the great research they're doing. So from the, you know, like in any university, it's faculty who decide what they want to work on. And I'm really just reporting from a grassroots effort what the people are working on and putting it, you know, into one big picture. The Data Science Institute itself, as I mentioned, has, so let me back up and say, when I first joined Columbia University in 2017, it was at that time, the Institute was elevated to be a university level and a university-wide institute. And so I felt it was my mandate to make sure that I showed the breadth of data science and the partnerships across the university to tell everyone that I wanted to be their collaborator. So I really went broad, and I think I've succeeded. So in the next coming years, I want to focus some of the efforts of the Institute, because we can't actually do everything. I can tell stories about everyone's work, but the Institute itself can't do everything. And that's why I've identified those 5 focus areas. Foundations of data science is really core to advancing the state of the art in data science. That is the first part of my mission statement, and also represents many of the faculty who are especially in the engineering school, and what they do. They do machine learning, they do computer vision, they do optimization, and just hardcore data science methods. And these other 4 verticals, if you will, climate and health and business and social justice, really represent some of the strengths and interests of the entire university. So for instance, Columbia University just created a climate school. So how could I not want to collaborate with the climate school? Because data is so important, not just in the science, but in policymaking and in law. We have a phenomenal medical center, medical campus. So we've been partnering with the medical campus, especially on looking at data and cancer. So that's a big focus for us. We just got 2 endowed chairs for research scientists who work in data and cancer. So if anyone is interested in applying for those positions, please let me know. And of course, being in New York City, business and finance is an obvious focus area, and we've got a terrific business school. And finally, social justice is something that really speaks to many of the most recent pressing issues of society, but also it's a long-standing interest and strength of Columbia University. So I don't know if I answered your question, Craig, but you gave me the opportunity to explain our focus areas.
No, you did. That's great. And we have a few questions from the audience. Let's go through a couple more, and then we'll have to take our break. So the first one's from Arnia Shokri, and she says, "Amazing presentation in the data visualization for hypertension. When you said 1/4 of the people have unique situations, do you mean that the combination of medications they use is unique? What if only one drug is used for treating an illness? How do you apply the decoupling?"
What I meant by unique is, I very too quickly actually explained how to read those visualizations. But each patient is given a sequence of drugs to treat that particular disease, in that case, hypertension. So one patient might be treated with drug A, B, C, D, E, F, and another patient might be treated with A, F, G, and so on. And what I'm saying is that 1/4 of the patients in this study were found to be treated uniquely, and that is pretty amazing. You would think around the world that there's a common treatment for something like hypertension. And that this is what is so eye-opening when you've got so much observational data.
Interesting. Great. So we have one last question we have time for. This is a question from Michael Pisani. It says, "I've been a big advocate of inferring causality from observational data. However, the recent experience with COVID-19 has led me to question utility versus double-blind trials. Many observational hypotheses, for example, vitamin D reduces the chance of getting COVID, were disproved with double-blind trials. How can we trust causal inference when we don't know all confounding factors?"
Yes, look, I have no silver bullet for the confounding factors problem. I completely agree with you. That is, of course, the starting point of classical causal inference. And it's one reason that I was trying to promote multiple causal inference, because the assumption is weaker and because the assumption is testable. But it still means that you have to think of confounders. And in that multiple causal inference case, that there's no single unobserved confounder. So there's no silver bullet. I very much like these other techniques that people are studying. I think the synthetic control is very inspiring. And there are other techniques that I know economists use in a very, which are just really instances of general causal inference, and they've been, of course, using that to their own worth. I wanted to mention another thing about COVID-19, and this was actually related to Odyssey. So the European equivalent of the FDA actually based some of their policies. One was the there was this early days, people were thinking that the hydrochlorine, hydra something or other, was an effective combatant to COVID-19. And by looking at Odyssey data, the equivalent of the FDA in Europe said that was a hogwash. So they actually instituted a policy that told doctors don't go there. The second is actually more recent, and there was obviously a lot of controversy, and there still is, on the AstraZeneca originally and now the Johnson & Johnson for blood clotting, and the risk and so on. In the very early days, when there was a lot of concern about AstraZeneca and whether it leads to blood clotting, the European equivalent of the FDA looked at the Odyssey data and concluded that it was that the AstraZeneca vaccine was still worth, using, despite the observations about blood clotting. Since then, of course, there have been more situations with blood clotting, and also Johnson & Johnson has had some similar problems or issues. So I think that this is still an ongoing debate, although we understand, with the CDC and so on, and that we should trust taking the Johnson & Johnson and the AstraZeneca. So all I'm saying is really that the Odyssey database, with that incredible amount of observational data, is already having an impact on policymakers.
Great. Thanks for the terrific talk, Jeannette. I think there's a few more questions pending, but I think we're out of time. We need to take a break now before we start our next session.
Okay. So, thank you, everyone. Bye-bye.
Thank you, Jeannette.
And so we'll resume again here at 10 o'clock sharp.
Thank you, Craig. See you all soon.